Oh, okay. Give me a sec. I'm going to get this set up. I'm gonna test the audience mode here so that the audience is able to participate in these calls. I'm having my friend come and test this because last time we tried to do it, it didn't work. So just hang in there for a sec, and I will start the stream pretty soon. I should have some kind of music that plays or something so it's not boring. Okay, my friend has joined. He told me he joined, but I don't see him. Oh, wait, okay. Seems like he's having a connection issue. Hang in there. Let me see. I'm gonna put up some graphics. All right, now everyone watching this knows. Yeah, he's connecting. I'm texting him right now. Oh wait, keep this up. Show. Oh, he got it working. Well, kind of. I see him in the studio here. Okay, did he send a message? Oh, wait, okay. Oh, here we go. Oh, I see. Okay. Yeah, this is his message. Yeah, so messages work. I know that. But can he call into the show? This is the question, because I want people to be able to join the conversation. So we're testing this feature here before we get started on the stream. This is what I said to him. We're just waiting. Let's see what these tunes are while we wait. Interesting. Can you guys hear this? I think you could hear that. Oh, wait, I think you can hear this. Interesting. I'm just putting the sound effects here on the stream. Oh, interesting. I'm using this platform, Riverside, in order to do the streaming, and this is a built-in video. So it seems like I can actually upload videos into Riverside. That might be better than reacting to them on YouTube. Okay, my friend just got back to me. Okay, he's having a technical issue joining. I'm just texting him. Okay, so anyway, let's not do this right now. So he's gonna go and try and get these technical issues figured out so we can have audience participation. But I want to get to the actual live stream content. So let me share my screen. As usual, we're going to be watching some videos and reacting. So last time we watched this video by Balaji Srinivasan talking about Silicon Valley's ultimate exit, and it's just a really important idea to show how technology and politics converge. So I think that that's a very important talk. It's foundational. And if you see a lot of the really cool things that Balaji is talking about today, this talk was 11 years ago, and he had already been thinking very deeply about these types of issues. So I recommend at least going and searching this, watching it yourself. It's very interesting. And if you want full commentary on it, go and see my previous streams. You can subscribe on YouTube to my channel. It's LZRSCG, or you can just follow me on X, which is where I'm live streaming this. So, okay, I'm just gonna set up my monitor. All right. Okay, so now this talk, I think this is a super important talk. This is basically like, for context, Andrej Karpathy was at one point the head of, I'm not sure his exact job title, but it was something like the head of AI at Tesla. And so he's going to talk about, how AI has evolved over the years. But what he noticed was that building self-driving was one of the most difficult engineering feats ever in software development. And he noticed that this process was fundamentally different from the way, like, in order to build such a complicated piece of software, the team at Tesla had to do something that's fundamentally different than the way that anyone had ever built software in the past. And he kind of started realizing that when people are building these really powerful applications powered by AI, that actually they're doing something different than, there's a new way that they're developing software that's fundamentally different and fundamentally more powerful. And so he goes and he lays out this idea of software 2.0, which is like software 1.0, but except that would be the old software, and then software 2.0 is this new thing. So it seems like my friend is back. Okay, so now before we dive into this, let's see if we can accept a call in from my friend to see if this feature works. So bear with me for 1 second as we test this. Sorry for the delay. Play this music. This built-in music is kind of good.
Powered by Riverside.
Powered by Riverside FM.
Okay, well, for now, we'll just continue watching this, and we'll see if the call-in feature works later. Okay, let's watch Andrej Karpathy, the GOAT.
Great. So I'd like to tell you that I see as a transition in how you write. So as referring to software 2.0. Actually, to tell the story correctly, I actually have to go back quite a bit of time, about 1 million years back. This is us throwing rocks at each other 1 million years ago, but we're actually a pretty clever species. We discovered how to control fire, and developed our agriculture, and then we started building machines. We use those machines for computation, and we transitioned the computation from mechanical to electrical. And then here we are.
It's funny that tech bros always need to go back and make the point from the beginning of human history all the way up until today. I do the same thing.
2018, and we're writing software. And we've built up pretty complex software tools. And the way we've come about all of this progress is that we actually apply a single approach to advancing all of these applications. So first, we identified some kind of a problem, and then we break it down to subproblems, and then we create algorithms for every one of those subproblems, and then we stack them together up into a system, and then those systems can actually get pretty elaborate and pretty complex. And so this really kind of approach by decomposition has worked for us very well, and we've been able to create kind of amazing progress.
Okay, so let's break down what this is. Okay, so essentially what he's saying is that the way that we have traditionally built software is that we have a very specific set of instructions that we want to run. And so the way that this typically works is you have a problem and a solution, something you want to solve. Like right now, we're streaming, you're watching this live stream. So I'm using Riverside, so they have some servers, and X is where I'm broadcasting this to. So X has some servers, and there's a protocol, RMTP, that sits in the middle, and there's these media servers, and there's encoding, and there's all this stuff. I mean, we couldn't possibly cover everything in this stack. But each piece of each piece of software that's running on all of these computers has been designed with something specific in mind. Like there is a RMTP server that is built to handle the RMTP protocol specification. And you can go and probably look this up and see like everything that server needs to do. And so the idea of it is that it would send and receive live video. And so like, let's say you're building this, you would create the specification, you would create the plan, and you would break apart each piece of this plan into actionable steps. And then you would have software engineers go and build this whole thing line by line. Every single line would be written down by somebody. And you might start off at some kind of higher level and say, here are the pieces. There's this component that sends outgoing data. This component receives data. This component stores data. Here handles the errors, and this is the logs. You might kind of scaffold this big picture. And then you're also going to go in depth and handle every single edge case. If the server doesn't respond, then you do this. If it does respond, then you do this. If you have extra data here, then you handle it this way, and so on and so on. And so basically, in order to do this, you have to understand the problem. So we devised a protocol for transmitting video. And then when we understood how this system was supposed to work, and since we understood it, we were able to then make software that did those exact steps that we intended to do. And maybe that's a little bit abstract, but the point is that if we've coded something, we being humanity, people, engineers, if we have coded something, this is a process that we collectively understand. And there's big code bases where nobody understands the full thing. We're not saying that a single person necessarily understands exactly what all software does, but in aggregate, if you take all the software developers and combine their knowledge, you would have a full picture of what any given piece of software does. So, let's continue, but I just kind of wanted to explain what he's talking about here. About you take a problem that you understand and you decompose it into its parts, and you build a system that combines all of these parts. And so you have a fully intelligently designed system made by humans. That's software 1.0. That's how we've been building software up until this on this matter.
Very well. And we've been now, unfortunately, the last few years, we've come across a few problems that actually make it really difficult to apply this methodology that has been so successful for us historically. So in particular, one problem that I'm quite familiar with is computer vision. And it's actually really difficult to take a million numbers that describe that image and turn that into a concept like a cat or not. And so this approach by decomposition and by engineering the solution is actually not working extremely well. So it's not for lack of trying. People have kind of tried to decompose computer vision. So
let's just go, what does this slide mean? So he said there's like millions of numbers that make up this image. So what exactly does that mean? Well, you can think of this image in a sense as a grid, like think about, you have a piece of paper, it's two-dimensional. And now think about back in high school when you had these graphs, X and Y axis, and you plot something. So every single point on the X and Y axis was a coordinate. So there's like a position along the horizontal and the vertical. And so that's what a screen is. A screen is a bunch of points, and each point is called a pixel. So you might have like 4K or 1080p. That's talking about the number of pixels that are on the screen. And so this image is, in a sense, a 2x2 grid, or not 2x2, but a two-dimensional grid of colors. And so like if you like zoom in on any given point here, you're gonna see that there's a color at each point. And so, I mean, that's a little bit of a simplification, but basically, I mean, at the end of the day, that's what an image is. It's a bunch of numbers. And that's what the data file essentially contains. And you could think of it as like one big number, or you could think of it as like a grid of numbers. However you want to think about it, there's lots of different mental models for this. But the point is there's nothing, this looks like a cat. It's very obviously a cat. But how do you exactly just look at a bunch of numbers and manually write some sort of code to actually understand that this set of numbers is the set of numbers that corresponds to an image of a cat? It's a very difficult problem. How do you break that apart? Like you like, if we think about how do you identify a cat, and he might talk about this, but let's say that we're talking how do you identify a cat? Well, you'd say it has ears like up here and stuff like that. That is not like, how do you identify the ears as part of this array of numbers? That's a non-trivial, it's a very, very difficult problem. It's very hard to like look at this image and understand what is the essence of a cat, and how could we determine which images have a cat and which images don't have a cat, because this is not the only way that cats look. Cats also can look very different. So I think he's going to get more into this, but I'm just trying to explain to you a little bit of extra context and why it is so hard to write code that will reliably predict if something is a cat or not.
It's not for lack of trying. People have kind of tried to decompose computer vision. So we've come up with a theory of how we're going to break down the problem. If you'd like to recognize a human, maybe you'd like to recognize the parts of a human first, and we're going to go through several stages of processing, and we're going to try to engineer it. Unfortunately, this doesn't work very well because there's so much variation in what this looks like. Instead, in the 1990s, exactly good book. So we are trained, that's how we make progress. And then we have a bit of machine learning on the top, like training a super vector machine. And then we figured out in 2012 that actually we want to step back and not design those features. We actually just want to lay out a skeleton of the architecture, of the convolutional network architecture, and we want to leave much more to the optimization. In particular, we're optimizing over the weights of that network, and we're training those features. And so we're stepping back, we're designing less, and things work better. Now, we're still designing the architectures, but some of the most state-of-the-art techniques for ImageNet actually step back even more, and we're actually optimizing over the architectures now. So we do even less design. We don't even trust ourselves to lay out the architectures.
Okay. This is a pretty, okay, let's dive into this. This is pretty technical. So essentially what he's saying is, like, if you go back here, like, let's look at these images. I'm trying to parse exactly what images he put. Was there something before this? Oh, here we go. So essentially what you would traditionally do is you would have a variety of different things that you look for. And you would try to extract what they call as these different features of the image. So like here they have some heuristics for looking for arms and forearms and hands, and like they would detect edges, and essentially they would try to get different layers of how they parse and interpret these images. And by combining these, you could then build up with some confidence, you could see if it matches the patterns that you expect. And so they would go and they would like so for example, you would go and you'd say, okay, here's a cat, and then these are the cat's ears, and these are the cat's eyes, and you would try to find things that you would try to extract individual pieces of the thing of a cat. And you would then, when you have enough of those, it would come together and give you the idea that this might very well be a cat. But what he's saying is this didn't work very well. Instead, what happened is over time, instead of extracting features and doing all of this manually, instead, the trend is to just putting it more and just doing more and more compute, and not actually telling the AI that you're training what these different features are. You let the AI actually extract the features themselves. So over time, let's think about something that's a relatively easy problem, no, not easy, but a relatively easy problem to understand, like self-driving. So there's stop signs, there's stop lights, there's lines in the middle of the road in self-driving when you're driving. And so a self-driving algorithm needs to understand these needs to understand what is going on the road. So the types of things that they might have done previously was they would create a stop sign detector. They would create a stop light detector. Is it a green light? Is it a red light? Stuff like that. And then they would combine all of these to help orchestrate, they would combine all of these as part of a larger algorithm that would facilitate self-driving. And over time, the thing is, today, the way that they train Teslas, this talk precedes this, but today, they don't do that to my knowledge. It's completely trained end to end. They actually just have a feed of video of Tesla's driving and all the control data for the car, and they take that and they just train the AI on that raw data. So they are not necessarily pointing out to the car, oh, this is a stop sign, this is a speed limit sign. The computer is able to extract those important points itself, and it's able to infer that from the footage of driving. So let's just continue watching, because he is going to get into this stuff and explain it a bit more. But I know this was just pretty fast, so I wanted to go and dive a little bit deeper.
Engineering tools to the problem, to engineering the features, because that's just how we are trained, that's how we make progress. And then we have a bit of machine learning on the top, like training a super vector machine. And then we figured out in 2012 that actually we want to step back and not design those features. We actually just want to lay out a skeleton of the architecture, of the convolutional network architecture, and we want to leave much more to the optimization. In particular, we're optimizing over the weights of that network, and we're training those features. And so we're stepping back, we're designing less, and things work better. Now, we're still designing the architectures, but some of the most state-of-the-art techniques for ImageNet actually step back even more, and we're actually optimizing over the architectures now. So we do even less design. We don't even trust ourselves to lay out the architectures. And this is working well as well. So really, we're seeing this trend in using a specific example of computer vision, that the better you want the thing to work, if you have an evaluation criterion, like the loss on your test set or the accuracy on your test set, then the best thing to do actually is to step back, design less, and leave more to the optimization. So really, the way to look at it, I think a good kind of framework to have in mind is that
this is important. So I want to just go back on this slide before we go on to this next important slide. But like if you look at this, right, this is the amount of over here on this axis, as you go this way, there's less code is written by hand. And here you have more data and more compute. So what they're finding is that you're able to do like less handwritten code, but you can trade that off with more compute. And it's not clear to me why this is convex, but essentially I think the idea is that the performance does actually increase exponentially as you I'm not sure if that's true, but there does seem to be like by adding more compute, you far surpass what you're able to do by hand. I think that's the best way of interpreting this. But let's continue, because this next part is very important.
really the way to look at it, I think a good kind of framework to have in mind is that if you'd like to design the code yourself, this is software 1.0, you sit down and you write some Python or C++, then you're going to identify some piece of the program space, you write an algorithm, and the algorithm can't be too complex, so it's somewhere around the origin, because we're finite people. And so that's one solution, and then you can evaluate it, and then you can iterate on your algorithm. When you're approaching this from kind of the software 2.0 perspective, you're instead specifying a subset of programs that you're going to search over. So a convolutional neural network architecture, you're basically identifying a piece of the program space that you are willing to search for the solution in the optimization space that works well with data or on your problem. So, so the optimization really writes the code. We only identify a region where we should search. And so this is kind of, I had a tweet a while ago, and the tweet said, gradient descent can write code better than you, I'm sorry. And people are kind of confused about what that meant, but this is kind of like what I meant, is we don't write the code ourselves, we just lay out the skeleton, we don't trust to write the code, don't trust ourselves to write that code. And so this.
Okay, so let's break this down. So, okay, think about, this is called, like, think about this as the program space, which would be all possible programs, meaning all possible software that could be written by humans, or even not by humans, just in general, that could run on your computer. And so you could come up with a very simple piece of software, like Hello World is an example for most beginner programmers. They just make it print out the words Hello World. Or you could have a very complicated piece of software, like a self-driving car, something that's intelligent and can do, or ChatGPT, it can respond to any message. These are very complicated pieces of software. And then there's things in between. There are, for example, like a social network, like x.com. There's a lot going on there. There's likes and follows and recommendations and all of these things. And the point is there's a spectrum of complexity. And so if you're gonna make, like, anyone could do Hello World by hand. You just type print Hello World and it will work. That's very simple. You could build a very complicated piece of software like Google search or the X algorithm or whatever. You can build all of this by hand, and it's difficult. It takes teams, it takes years, but over time you can refine it and make it good, and it's possible to build. But if you go towards the frontier of this circle, there are the complex software lives over on this outer rim here. And so Hello World is here. This is very simple in the middle. Here is some just, whatever is traditional software 1.0, but is complicated, like Salesforce or something. This is difficult to build. There's a whole company had to work on it. The engineering behind it is very difficult. So this is software 1.0. But so this is complex. Like, don't get me wrong. One person could not rebuild all of Salesforce's software stack themselves. It's complex. You need an organization. It's very difficult. It's competitive, a competitive market for this software. But so it is complex, but it's as complex as humans can manage to do by hand. And remember, going back to what he was saying, this involves decomposing the problem. You have to understand the problem in order to build software 1.0. So, for example, 1 second, it seems like my friend might be trying to call in. Because one of the goals here is we're trying to see if we can allow audience participation in these streams. So so far it hasn't worked for people, so I'm trying to get my friend to call in so we can see if this actually works. So I will resume this explanation in a second. I'm just going to tell him I don't see his request. I see his message, but not his request. I'm gonna call him.
Hey there.
Hey, are you?
I can
Do
see
you?
you fine at streaming. It seems, but when I click continue, I'm like seeing like where I'm setting things up. I fill out my name, what you call me, and then when I hit start live call, it seems like a dead button. So does back. It seems like the JavaScript for the start live call button on Chrome is not really working. Earlier, when I was clicking, it wasn't doing anything where like crashing my computer. It was like immediately using up all the battery or something. So I did it on mobile, and so there's an app for it. So what was saying I could do it on mobile. It's currently connecting me to Studio
Interesting.
on the podcast.
Yeah.
App. Yes.
Yeah, I had the same problem when I was testing it. I thought maybe it was just like because I was on the same computer that I was streaming from. Did you try it in Chrome? What are you using? Are you using Firefox?
No, I'm using Chrome. Firefox is not trying to load at all.
Yeah.
I'll try Firefox again in a second.
Do you have like a lot of like privacy stuff installed on Chrome?
On Firefox, I have more. Okay, hold on. Mobile app is working out. Let me try. I'm gonna hang this phone up real quick.
Okay. I really hope that we can get people to be able to join these calls. It'll be way more interesting. I mean, I'm going to ditch Riverside if this doesn't work. I'm not going to continue using this for streaming. We'll be right back. I just want, in case anyone's tuning in, I just want to let them know why I'm not talking much right now. Yeah, okay. Seems like you can't call in via the mobile app. All right. I think it just doesn't work. Okay, well, I'm going to continue. I'm going to continue what I was saying here. Okay, so getting back into it. So, point is, a simple program like Hello World is here. A more complicated software, such as just whatever Instagram or something, right? That's here. An organization can come and make this. It's very difficult, but they can do it. But then there are things, and the reason they can do it is because they know what the customer wants. They talk to customers, they make a plan, there's product managers. They basically say, we want to achieve this specific set of features. And they will break down exactly the features that need to be built into pieces. And they will assign this to engineers, and engineers will create it because it's an understandable piece of software. Now, when you get to something like ChatGPT, that's another story. That's very complicated because this is not just information retrieval in some very formulaic sense. Like a Google search, it's very complicated. It's the most complicated software humans have ever created, Google search. But it is fundamentally, it's simple because what you're doing is you're just finding the results that are stored somewhere. There's queries and there's ways that map the queries to some kind of, you could imagine like some kind of index, so to speak. I mean, I'm oversimplifying it, and I don't actually really know how Google search works, but I'm just kind of giving you a hypothetical explanation for this. It maps it some kind of index in some kind of data store, and then and it's not very sophisticated. So it's like a heuristic. Like you do a Google search and it doesn't necessarily answer your question. It's just something that's vaguely relevant to what you typed in. So like a very dumbed down version would be if you type the word apples into Google, it could look up all of the different web pages that contain the word apples. And then it could put those as the results. Now, if you're asking a question, it might not answer your question. If you're asking what are all the different types of green apples, it may not know, it may not give you that information, but it will at least be relevant to apples. So that's what Google search is. It's a much simpler piece of software. Now, ChatGPT, on the other hand, is much more complex because you're not just retrieving information in some kind of vague heuristic manner. What you're actually doing is you're trying to create a high quality response that's understandable for any imaginable question. That's crazy because you have to actually then list out all the types of apples if that's what's asked. And how would you ever know that someone would ask such a question? So you couldn't possibly like write all the answers and questions in advance. There's an infinite, not really infinite, but astronomically large number of potential questions that can be sent into ChatGPT. And so I'm just texting my friend about him joining. Just 1 second. So anyway, the point is that ChatGPT is way harder to create. So ChatGPT lives somewhere here on the frontier of extremely complex software. And so that's here. So let me take this off, this badge. Okay, so let me keep playing. Let's go to the next slide.
So that's one solution, and then you can evaluate it, and then you can iterate on your algorithm. When you're approaching this from kind of the software 2.0 perspective, you're instead specifying a subset of programs that you're going to search over. So a convolutional neural network architecture, you're basically identifying a piece of the program space that you are willing to search for the solution in, and then the optimization actually finds a part of that program space that works really well on your data.
Okay, so basically, what this means is ChatGPT has very specific code that executes on a computer. And we know this because it works. So I'm on my computer, I type in a question, it goes out to OpenAI servers. OpenAI it runs this software and it infers the answer and it sends it back. So there is some software that exists that is able to answer all of my questions. Well, it turns out, so that is just software, to be clear. Like you can say, oh, it's AI. Yeah, it's AI, but it's software. It works, it runs on a computer. We got the computer to answer these questions. How did we do it? We did not code it by hand. That would be way too hard because you would have to think about what are all the things they could ask? How would they ask it? What are the different versions of that same question? How do you, and map all of that? It would be impossible. It would be impossible. And not to mention, I mean, how much text would you have to store for that? For every possible question, you'd have to store the answer. You'd have to, like, it would be ridiculous, right? And yet AI is very compact. It can answer almost any question, but it doesn't take up that much storage or memory in RAM when you run these models. Like you can run some of these smaller models on your laptop. You can run some of the bigger models on you don't need to have a whole data center even to run even the state-of-the-art stuff. So it's highly efficient and it works. How was that created? It wasn't created by hand. It would be way too hard. You can't understand the problem of answering all possible questions and decompose that and code that by hand. That would be way too difficult. So what do they do? Well, they do optimization. I'm just responding to the chat here. Okay. So anyway, so let's continue. Let me go to this next point that he makes, because I'm going to explain what he means by searching and optimization in just a second.
or on your problem. So the optimization really writes the code. We only identify a region where we should search. And so this is kind of, I had a tweet a while ago, and the tweet said, gradient descent can write code better than you, I'm sorry. And people are kind of confused about what that meant, but this is
Okay, well, let's see what he says about what it meant, then I'll explain.
kind of like what I meant is we don't write the code ourselves, we just lay out the skeleton. We don't trust to write the code, don't trust ourselves to write that code. And so this is working well, not just in computer vision, but we're seeing this across other disciplines, machine translation, speech recognition, and so on.
Okay. So what does this mean? So what is gradient descent? Gradient descent is a really simple concept that you would just learn in like college math. Basically, you have, well, the way I like to think about it is if you have like a mountain range or something, right? And you drop water, like it's raining on, there's a mountain and it's raining, the water will flow down to the valley. And let's say there's like 2 mountains and there's a valley, the water will flow and fill up the bottom. So what is that doing? That's finding a minimum, a local minima in that, on the earth, meaning a low point. So if you look at the top of a mountain, on a mountain range, that's like a maximum point, a highest point. And if you look at the bottom of a valley, it's like the lowest point. So someone who's climbing a mountain is finding a maximum. And rain that falls down to the bottom of the valley is finding the minimum of that surface. And so there is a sense, so like how would you do this? Like how does it literally work? So rain falls, rain is on the mountain. It's getting pulled downward by gravity, but it hits the ground. It can't go straight down. So it doesn't, I mean, it might bounce up for a second, but generally speaking, what's going to happen? The water will flow on the path towards that downward area. Now, you might have a mountain. Maybe I'll try and do this with my mouse just to make this more clear. Like you might have a mountain that goes up like this, and then down like this, and then up like this. Like you're able to see this. So up, down, up, down. So there's like a little mini peak right here. The water might go here, get stuck in this low area, and never get down here if it was raining up here. I hope that makes sense. I wonder if, can I draw on this? I don't think I can. I should be able to, but I'll figure this stuff out as I get more experience with streaming. But the point is it will go to a low point. You're not necessarily guaranteed to go to the lowest point, but it will go to a low point. How do you climb a mountain? Let's think of another example. Maybe this is more clear. How do you climb a mountain? Like just think about it. You're trying to go to the highest point. Let's say you want to climb all the mountains on all the continents. So you have a thing where you say, I want to go to the highest point on every single continent. People do this. What are you doing? You're doing gradient descent or gradient ascent. I don't know if there's like a difference, but you are ascending a gradient, meaning like a transition. I mean, what is that? Like a gradient would be like a curve. I don't know, whatever. The point is you're ascending a mountain. You're going up from a low point up to a highest point. And your goal is to go to the highest point. So what do? Let's say you don't have a map. Let's say there's no GPS. You're just on the mountain. What do? You go toward the direction of the greatest point. You walk up. You look, oh, this is the direction that's increasing, so I'm going to walk that direction. And you don't go down. You don't walk down the mountain. You walk up as much as you can. You know what direction. You see the mountain is going up and I'm walking up. Okay, so what does this have to do with gradient descent? So that's basically what gradient descent is. Gradient descent is when you have some kind of curve that's graphed. You go the direction towards, whether it's increasing or decreasing, you're either trying to maximize or minimize. the curve. So you're going towards the local maximum or the local minimum. And depending on how steep the curve is, you might like let's just say like you have to go up a mountain, you're gonna have to it's gonna be harder to take a step. So you're gonna put more energy into climbing up the mountain. So when you're doing gradient descent, basically it's basically this algorithm where you go and you find the maximum or minimum of a curve by going in the direction of the descent at the point that you're at and going with a magnitude. You're basically each time that you run this algorithm, you get closer to this maximum or this minimum. And so that's essentially how AI works. AI, you're essentially quantifying the amount, the degree to which the AI predicts the wrong answer, and that is the error. And then you have like this, you can think of this as like a shape of this error, and what you're trying to do is you're trying to minimize that error. So you're doing a gradient descent in a way that minimizes the error of the problem. Maybe I could have explained that a little bit better. But the point is that what this does is this actually adjusts every single time you train the AI. You are searching for a new solution. So when you run here, let me go back. So you start out here and you are putting data through the AI. You're training it. You're giving it training data, and it's going to make predictions. And then you're going to adjust the neural network based off of how correct that data was. And that's going to actually then change the content of the neural network. So what you're doing is you're changing the neural network, and you're putting more data and more data and more data, and every time it steers it in the right direction. Like just think about like each time that you train, it's like taking a step. You're climbing a mountain. You're trying to go to the top. And so what direction do you walk? How do you walk there? Well, every time you look, okay, well, there's the top. I'm walking up the mountain. And so that's how you find the peak of the mountain. It's like you're searching for it, but you know where to go because you're able to follow the mountain. Like if I said, go find the town down the river, how would you do it? You would follow the river. You don't necessarily know where the town is, but you know it's down the river, so you follow the river, right? So that's essentially what AI is doing, is they're iteratively putting data through the neural network, seeing does it predict it correctly, and for the degree to which it predicts it incorrectly, like let's say it says go left, and that was very wrong, then you know to go right. Maybe these are bad intuitions. Maybe this is not the best explanation. I should like prepare a way of explaining this that's way better. And maybe do a video on that specifically. But the point is that the neural network adjusts over time, and by putting more compute and more data into it, you're actually searching for for a very good piece of software. And the end result, let's say this is the end result, this is ChatGPT, this is going to be able to answer all your questions, but you don't know how to answer it. You don't know how to answer all these questions yourself. You don't know how to build software that answers any given question. But you know that if you put enough text into this algorithm and you do it enough times, that it will eventually correct itself to find the code that would have generated the answers to those questions. So let's continue.
A region where we should search. And so this is kind of, I had a tweet a while ago, and the tweet said, gradient descent can write code better than you, I'm sorry. And people are kind of confused about what that meant, but this is kind of like what I meant. It's we don't write the code ourselves, we just lay out the skeleton. We don't trust to write the code. Don't trust ourselves to write that code. And so this is working well, not just in computer vision, but we're seeing this across other disciplines, machine translation, speech recognition, and so on. And it's not even constrained to data sets necessarily. Anytime you have an evaluation criterion that you can evaluate, such as playing even a good game of Go or chess and winning, you can actually apply this methodology. So you can either go on and write C++ and Python and complex repositories of code, which is kind of the stockfish approach, or you can step back and you can say, okay, I don't know how to write a Go playing program, so I'm just going to search the program space, and you can actually discover through optimization by paying in compute the much better algorithms in that space. And this is not even necessarily restricted to neural networks. You can also search over, say, assembly programs, like anything that works. If you have an evaluation criterion that you can repeatedly evaluate, then you're better off not designing. You're better off just stepping away and paying in compute to find programs that work really well. So I'm the director of AI at Tesla, and we're applying this methodology to kind of get self-driving cars to work really well. So we have, at Tesla, the largest deployment of robots in the world. We have about 250,000 robots, and our job is to try to make them autonomous and drive well. Now, when I arrived at Tesla maybe about a year ago, we basically have this software stack. The software stack is actually quite simple in terms of the code. There's a number of sensors that stream into the stack over time, and we're only trying to predict two scalars. We're trying to predict the steering and the acceleration of this vehicle, and we're trying to keep it in lane and so on. And when I arrived, you have this like meld of code. Most of it was a huge C++ repository, but then of course there's a convolutional neural network doing some of the base visual recognition. And over the last year, we've basically been porting some of that code to the 2.0 stack. And we see that there are improvements when you actually adopt this approach and when you get it to work really well. And so this is, the red is the code that we've written, and the blue is the code we've discovered through lots of compute. So just to give you a concrete example of this transition and what that looks like, suppose you want to detect if a vehicle is parked or not. This is something we want to know because of the control algorithms. So one approach you might think of, if you, again, are in this mindset of designing solutions, is you might say, okay, well, the neural network is giving me some kind of bounding boxes, and now a car is parked if, okay, so now I'm designing, right? So a car is on the edge of the road, and maybe it hasn't moved for a while, and maybe there's a pattern to the cars. And so this is not the right way to approach it, I think. It's, you're designing, and you shouldn't trust yourself to write that code. Instead, a neural network says so. And we see that it's
Okay. So basically what he's saying here is let's go back to all these different slides. Yeah, I mean, this is what I was saying. So maybe his explanation might have been better for you guys. But he's just giving examples of that you just need to, this approach works basically. And so now he's saying, okay, Tesla does this, and they have a significant AI effort. I mean, self-driving cars is the biggest and oldest effort in AI, period. Like ChatGPT is a new kid on the block, these chatbots, LLMs. But, and this is before, he did this before that revolution happened. And so what he's saying here is, this is the code for their self-driving algorithm. And a lot of it was written by hand. And there was some AI, but there was also a lot of manual code that was written to kind of glue that AI together. And like, who knows, like maybe they had like a map that contained the speed limit, and they would retrieve that speed limit and throw it into, I don't know if this is true, they might throw that into the algorithm, or they might even manually say, like, if the speed of the neural network is higher than the speed limit, then don't go that fast, or something. Like, they could have like written that code. Like, that code is something that can be written. And they would, maybe traditionally they would just use the AI to, for example, stay within the lane or something like that. I mean, there's a lot you can do. Like, you can kind of say, okay, the car is like, here's the lane, and you can if you can identify where the lane marker is, maybe with AI, you can then make sure that you're driving in the middle of the lane by calculating the space between them. You can do all that kind of stuff manually. So that's probably what they were doing a lot of the time. But they just were using like some basic image recognition, like, here are the lane dividers. Here is a, let's detect a stop sign in the video, and then we can, once we know where that stop sign is, we can, do something along those lines. So there was like a lot of logic there that was manually constructed. And then what he's saying is, over time, he's seeing that software 2 is eating software 1. Like Andreessen Horowitz says, software is eating the world. Well, software 2 is eating software 1. So this, he didn't say that, I'm saying that, but this was their entire code base. Now more of it is this blue area, which is software 2. And so what he's saying is, actually, we're able to rip out the code that we wrote painstakingly by hand, and we are able to replace it with something that's trained end to end by just putting compute and data into it. And not only is, does it replace what we wrote so we didn't have to write it by hand? It's actually better. And by the way, today, Tesla self-driving is so good. I don't know if you guys have tried it. If you had an idea about it from several years ago, you should try it again. It's very, very, very good. And I think like this is the old talk. Now I bet it is so like vastly blue and maybe a little bit of pink in there, but mostly blue. And this is something that George Hotz talked about years ago too. He predicted that Tesla would go this direction. And yeah, well, we can maybe talk more about that another time. I'm gonna also react to one of George Hotz's talks at another point. But let's continue. He said more stuff. So okay. So this is the example that he gave. This is a great, clear example. Basically, there's all of these criteria, like how do you know if these cars are parked? I mean, like you have to look for these bounding boxes, like this is the bounding box. And you try to calculate the space and if it's in a location that's friendly to parking or whatever, right? You had to do all this logic. I mean, that's ridiculous. To get that to be reliable, because sometimes people are parked in the middle of a dirt road, like, or just parked in a road for no reason, or there's construction, so there's like construction tape or whatever, or there's something blocking your view. I mean, you're gonna not be able to write a comprehensive, reliable algorithm that detects if things are parked with no false positives, no false negatives, like something that's super reliable by hand. It's just gonna be very difficult. Like you can see, like just think about how would you tell someone that, like how would you design this? Like it'd be very difficult. But you can actually, empirically speaking, train a neural network to do this very reliably. And so this is a great example of that this actually works in the real world. So let's continue watching.
It's a much better approach. See that it's a much better approach because we've tried, and we've tried pretty hard. And so that's just an example of kind of this transition. And now in terms of like programming with the 2.0 stack, what does that look like? What are you actually doing? Where's the work? So what you might be familiar with, and this is where I'm familiar with as well, is when you're writing code, you're actually designing algorithms, you're measuring running times, you're engineering these, and you write out pseudocode like this, and you feel very clever when you get something really cool. This is not too much of what it looks like. In the 2.0 stack, the workforce splits in two. There's one large piece of the workforce. All they do is label data. So you have pretty complicated UI interfaces, and these people are putting bounding boxes and lines and so on these images. And in the process, there are little programming pilot because this code. So help out the software. They're programming the autopilot. Try to help them out with surrounding infrastructure. So we create the UI tools, we create the analytics around it, and we kind of.
I'm not sure about this, but I think some of this is a bit outdated even, because in theory, you don't really need to even label things to train a self-driving car. And I could be wrong about this. Like, please, someone feel free to correct me. But you could just simply get enough video footage where you just show that this is the video of someone actually driving, and this is, how they, like what the acceleration of the car and the steering of the car were at that time. And if you just feed that to a neural network, you could, it would internally extract all the different features and understand like what a stop sign means and all of that kind of stuff. So I wonder how much labeling they're doing now. Maybe they're still doing it. Maybe they did enough already and they can extract the important features, like you can like label stop sign and now the AI knows that that's a stop sign, or maybe they're just training it end to end these days without even like basically throwing out all this old work. But I think the point that he's trying to make here is you need a data set. And this is their attempt of building up a data set. And so they actually, instead of building the software directly, they built software to generate the data set, a high quality data set. And they got these labelers to go and label things within the video to make the data set better, so that the training could take place. And then with this data set, they throw this data set in and throw a bunch of compute with it. And through that, they use a neural network to search for the perfect implementation of self-driving. And I know they definitely do some labeling today, just to be clear. Like if you're driving a Tesla and there's a mistake, you can send in a message. And so they're looking at times when the Tesla messes up, and they're trying to identify these these classes of errors and stuff. So I'm sure they're doing some of that, but yeah, I'm not sure if they're just annotating every single vehicle on the road and every single sign and stuff like that, which is kind of what he's talking about here.
Insert a layer of intelligence around some of these workflows that they have to go through, and I'll go into that in a bit more detail. So really, my background is as a PhD student, and I spent a lot of time worrying about the models and the algorithms and how you actually train these networks. But when I kind of arrived at Tesla, there's been a little bit of a transformation in terms of like trying to actually apply this methodology and what that looks like in practice. My PhD is spent worrying about the architectures, but at Tesla, I spend most of my time just massaging the data sets. And this takes a huge amount of work, huge amount of effort, and you want it to do it extremely well. So just to give you hints at what this kind of why this is so complex to maintain this infrastructure. So number one, even the data labeling is highly non-trivial, as I found out pretty early. You might think this is pretty straightforward because we have some kind of an image, and we want to, of course, stay in the lane. So okay, so there's a lane line there, and we should stay in that lane. So this is the annotation instructions, even to the labelers. And then you go out to the real world, and you find all kinds of craziness. So this is somewhere in Europe. There's zigzag, and now you're suddenly really not sure. Like, do I annotate the zigzag? Do I go through? It's really not obvious. Or you find something like this. And then the labelers are confused, and everyone's confused, and now I have to like change the labeling instructions. It's kind of a craziness. Like, then what the hell is that? Why does it go on the side?
This is a problem with low IQ labelers. I'm joking, but obviously, you would label this and this. You wouldn't. That's decorative or whatever. But yeah, this one's a little more tricky, I would say, philosophically. But yeah, so one thing I was saying is I'm not sure the degree to which they do this anymore, where they actually label the lane lines, because I think that this is something that with enough compute and enough driving data, the car might actually be able to abstract. The AI might be able to abstract the idea of lanes for itself. And so you don't need to say, this is the lane, now go work with that and drive within the lane. You might just be able to give this footage and say, look, people, based on the training data, we see that people drive inside of the lane. So just drive inside of the lane. You don't need to actually have a concept of lanes. Now, I'm not sure how they do it, but I'm just saying, in theory, that is definitely the case. So these are some funny examples. So let's see.
Do I annotate with it, and then someone later worries about it, or do I annotate through it, and I try to put that in 2.0 stack? Like, it's not obvious where you put this code that has to worry about that little kink. Or you're trying to label cars, and you might think it's pretty straightforward to put bounding boxes around cars. This is very much not the case, because there's lots of crazy stuff in the world. It's not obvious if this is one car, or it's 4 cars, or it's 2 cars, because of the
It's 1 car.
Joint. Traffic lights, you might think it's just red, orange, green, and you put bounding boxes around them. But that gets really complicated really fast. So yeah, and you end up basically accumulating these labeling documentations that are hundreds of pages.
Well, some of this is interesting because it depends on where they're coming from. It kind of cuts off these lights. So you don't necessarily know where the car is in relation to this. But yeah, I mean, this does not really correspond. I guess this is a red light. Yeah, I don't know what this even means. This is pretty tricky.
to do some of these tasks right. And this 2.0 workforce actually has to be pretty highly skilled to even understand what you're trying to get them to label. And if they don't label it very well, then your network won't work very well. Speed limits are a complete disaster. I thought it was just a number. Maybe I'll run some OCR or something, but these truck during Sunday, I don't know. It's just gets AI complete extremely quickly. Like how it's not obvious.
AI should ignore speed limits. It's stupid.
So I've for a while. Kind of, if you're imbalances to be in check. So, for example, if we're trying to recognize whether a car has a blinker on, as you might imagine, the blinkers are almost always off. So if you're naive and you just sample your data at random, then you will get very few examples of blinkers actually being on or off. And so suddenly you have to worry about your data imbalance and chasing it and developing the tools to actually find all those rare examples that are very important. For example, orange traffic lights are another example. We have a huge amount of annotations for red and green, not as many for orange, and so the network struggles in those cases. It's not just about the labels, it's also about the data. So most of our data looks something like this, highway driving going forward. And then, of course, if you take a neural network that is trained on something like this and you bring it to an environment that looks different, that's not going to work very well. So either in this kind of environment or even in San Francisco where the roads do weird things, that might look foreign. And so now you need quite a bit of data to actually have a coverage and have a broad distribution. The other thing.
Yeah, that makes a lot of sense. I mean, again, I think a lot of this stuff is outdated because I don't think that they're continuing to do as much labeling. A lot of this is just end to end. But again, the point is that you need a data set. And then if you have the data set, you can use compute to make better, more complex software than a human could ever code. And yeah, I don't know what orange traffic lights are. I guess is that an American thing? This is not an American license plate. Yeah, I mean, if you're operating in the more places you're operating, the more difficult it is. I think that's one reason why it's good to be bearish on Waymo, because they're just operating in San Francisco and maybe one or two other major cities. So they do not have the breadth of diversity of data that Tesla has. And I've heard that they do remote driving. I don't know if this is true, but on X, people have said that they actually have remote drivers go in and they don't even necessarily use AI. Like people are remote controlling the cars at certain points. So that's crazy if that's true. Tesla self-driving is so good. I don't think anyone can come close to that at this point. Maybe AI. George Hotz, who was so forward-thinking and basically was talking about end-to-end neural network training without all of this feature extraction and labeling and stuff long before Tesla was doing it. Cool. So I'm going to do a part 2 on this because there's still a good amount to go in this video, and it's been a kind of a long stream, and the next time I want to tie this in with crypto. So I want to finish. We're gonna finish watching this. It's at around 12 minutes, and then we'll tie it into crypto because this is actually very highly relevant to crypto. But yeah, we'll see. Basically, crypto is part of software too. So this is a new class of software. AI falls into it, and so does crypto. So we're going to talk about that next time. And I'm going to come back with like a better explanation about some of this like neural network stuff, just because I wasn't really prepared to explain some of this stuff on the fly. So next time we'll do a better job of that. Cool. Thank you everybody for tuning in. I'll see you tomorrow, probably.